Hi, everybody. My name is Rachel Wooliver, and I'm a postdoc at the University of Tennessee in the Department of Biosystems Engineering and Soil Science. If you're just now joining us, welcome to the cover crop tour. We have another couple of great talks planned after this one, so I hope you'll stay tuned. Today, I'll be talking about cover crop mixtures and their benefits to corn and soybean systems. Before starting, I would like to acknowledge my advisor, Dr. Sindhu Jagajama, who I've worked with for the past couple of years and is the PI on this USDA-funded project. As you probably know, cover crops are one of the many ways to improve soil health in agroecosystems. By themselves, cover crop species from different functional groups provide unique benefits to agroecosystems. For example, legumes like clover and vetch can add about 30 pounds of plant available nitrogen per acre to the soil. Grasses, on the other hand, are great at scavenging nutrients from the soil, and so their residues help recycle them back to the system after termination. And brassicas, like radish, are great at reducing soil compaction and suppressing pests and diseases. Each of these different functional groups can also cultivate unique communities of species around them, both above and below ground. But when combined into mixtures, these functional groups hold the potential to be greater than the sum of their parts. That is, because each species plays a certain role in ecosystem functioning, and also contributes carbon to soils that are unique in both chemistry and quality, they can together build diverse soil food webs and ultimately healthy carbon-rich soils. Some critical players here, especially in agriculture, are soil fungi and bacteria that are important in plant nutrition and disease suppression. To explore cover crop diversity effects on agroecosystems, we're running a USDA-funded field project at the West Tennessee Ag Research and Education Center in Jackson. This is a no-till trial that we began in the fall of 2020 and is currently in the end of the second growing season of row crops. In our trial, we have some different cropping systems, including monocultures and rotation of corn and soybean. But for the purposes of this presentation, I'll be showing you averaged effects of cover crops across these systems because they do not seem to be showing different trends yet. In the fall of both 2020 and 2021, we sowed cover crops, which included different treatments ranging from no cover to single species, double species mixture, and a 5-species mixture. Overall, our goal is to look at how crop diversity influences soil carbon, but as you probably know, it takes time to see management effects on such a slow changing carbon pool. So today, along with some weed suppression and litter quality data, I'll show you some soil properties that are known to respond very quickly to management changes and are known to be precursors to changes in soil carbon. Of course, in both cover crop seasons so far, we've seen a lot of weeds, including primarily yellow rocket, dead nettle, and some grasses. And the photo on the right here shows a no cover plot in the spring of this past year, right before cover crop termination. Here are the data on weed biomass after the first and second cover crop seasons. Again, these are averaged across our different cropping systems. In both years, all cover crop treatments suppressed weeds relative to the no cover control. And the 5-species mixture does the best job at suppressing weeds in both seasons. Further, residue quality with high quality indicated by a low biomass carbon to nitrogen ratio was best in the single species clover and the 5-way mixture. This means that for residues, more nitrogen is being recycled back to the soil relative to carbon. Further, single species wheat actually maximized soil moisture after the first cover crop season. We think that this is related to wheat producing the most biomass in the first year compared to all of the other cover crop treatments. But by the end of the second season, the 5-way mixture maximized soil moisture. And this plot tracks plant available soil nitrogen since the beginning of the field trial through this past spring. You'll see that nitrogen didn't change much over the first winter. Legumes actually didn't grow as much as our grasses overall, and so much of the nitrogen was likely scavenged by our grasses. During the first row crop growing season, nitrogen begins to decrease as the crops scavenge it from the soil, but by the end of the growing season, the plots that had the 5-species mixture had the most plant available nitrogen. What this might mean is that the decomposition of residues in the end of the growing season provided nitrogen in excess of row crop demand. You'll see that clover plots have the most nitrogen after the second growing season, the cover crop season. Our legumes actually did really well during this winter, so their residues were likely able to release a lot of nitrogen into the soil at first. And finally, from soil microbial sequence data, after the first cover crop season, we saw that the 5-way mixture maximizes the abundance of arbuscular mycorrhizal fungi in the soil. Even though these results are only after the first couple of years of this field trial, and they are very preliminary, we are beginning to see that the 5-species mixture does the best job at suppressing weeds and providing multifaceted benefits to soil health. Hopefully in a couple of years' time, I'll be back to show you some more long-term results. Thanks for listening to this presentation. And if you have questions or comments, please feel free to email me.